Hi, my name is Abhinav, and I'll be presenting our work, Depth EquiVariAnt NeTwork for Monocular 3D Object Detection. This is a joint work with Garrick, Brazil at Meta AI, Enrique Corona and Armin Parchami at Ford, and Xiaoming Liu at MSU. Equivariance refers to the deterministic transformations at input, resulting in deterministic transformations at output at every layer of the neural network. CNNs are also built on the translation equivariance, and CNNs are equivariant to projected 2D translations TU of the ego camera. However, CNNs in general are not equivariant to 3D translations of the ego camera in the projective manifold. So our idea is to use depth equivariance in the projective manifold. So why depth equivariance? So vanilla blocks are for Euclidean manifold tasks, but are not for projective manifold tasks such as monocular 3D. Mono 3D is also a generalization problem, and equivariance improves generalizations for tasks in Euclidean, spherical, and hyperbolic manifold. Here we show that there is a significant gap or a generalization gap between training and validation performance from the baseline method GUPNet. And finally, depth remains the hardest parameter to estimate for monocular 3D. So how does this equivalence look like? So we show that like the depth translation is actually a scale transformation, and therefore we can apply scale equivalent convolutions. And this scaling transformation also is guaranteed to appear on the output of every layer of the neural network. So our corollary says that when a ego camera translates along the depth without rotations and the patch plane is approximately parallel to the image plane, the depth equivariance in projective manifold is the scale equivalence in the Euclidean manifold. So vanilla CNN we show here with a small toy example that it is not depth or scale equivalent because it shows some aliasing in general. Deviant constrains some of the feature maps, for example, these two, and helps getting better prediction. So how do we construct the deviant backbone? We use replace vanilla convolution by SCS convolution, replace the 2D patch by a 3D patch now, replace 2D pool by a 3D pool, and finally add some SCS max scale blocks as well. Our experiments use the KITTI, Nuisance, and Waymo datasets. We reach the state-of-the-art performance on KITTI test and the KITTI val speeds. In addition, we achieve significant gains from using this method in a cross-dataset evaluation setting, which suggests better generalization. We also outperform the baseline GUPNet on the Waymo dataset. We next quantitatively evaluate the equivariance error, and we find that like GUPNet has more equivariance error as the depth increases or the down scaling factor increases. Deviant has less equivariance error. We also show the performance of method using a demo video. We find that like the position of the boxes is especially stable, even though we do not use any temporal smoothing while drawing all these boxes across the frames. In addition, our method is also a multi-class method, so can also detect cyclists and pedestrians. So our project website demo and code are all up. Feel free to check it out. Thank you.